So in this example, you're given a particular, let's see, 3 by 5 matrix, and we're asked to find the dimensions of the null space and the column space of this matrix A. So either way, we're going to need the, whoops, keep almost knocking over the computer, the row echelon form for this matrix. And in fact, I'm going to get this thing all the way to the RREF form. I want to completely reduce this matrix, and then we'll analyze it. So I'm not going to copy it down. If you guys will forgive me, I'm just going to write the first couple of row operations over here. So first thing I would focus on is getting, I guess I'll turn this into a 1, especially considering the fact that I've got all multiples of 7 here. So I'll do -1/7 times row 3. And so that'll give me, yeah, it's going to take a bit of time to copy because it's a large matrix here. Okay, but so that'll just give us 1, 0, -1 in the last row. Great. So at this point we see we've got pivots in columns 1, 2, and 3. And so if we're thinking of this in terms of a system, then x3 and x4, x4 and x5 are free variables. Okay, like I said, I want to get this all the way to the RREF form. So I'm going to do 2 times row 3 plus row 1. 2 row 3 plus row 1. And then we'll have to do one other row operation. But let me, let's see. So our last row is 0, 0, 1, 0, -1. Okay, this row is going to stay the way it is. Yep. And then, so new row 1 will be 1, 1, 2 times this, so this is 2 plus -2, so that's 0. This will still be 2, and then 2 times this, so -2 plus 2, so this is now 0 here. Okay, one more row operation. I want to get a 0 in this position here, so I'm going to do -1 times row 2 plus row 1. And I know I'm standing in front of it. Here, let me move out of the way. So -1 times row 2 plus row 1. Okay, and so that'll give us, well, here I'm going to copy the other rows first. So the new row 1 will be 1, 0, and then, -1 times row 2. So 0, 1 plus 2, so this is 3. I'm losing track of, okay. And then -1 times this, so 2 plus 0, so this is 2. Okay, so there's the RREF form. And I think what I want to do, I'm definitely going to need more space. So I'm going to erase the work we did here. Well, yeah, okay, we can work from that. Okay, so first of all, let's focus on null space. So suppose, like I said, that this is the coefficient matrix for some system. I'll call the unknowns x1, x2, x3, x4, x5. And let's say, so with null space, it's augmented with the 0 vector here. Remember, null space is the solution set to the equation ax equals 0. So if that were the case, then if we solved for the basic variables, x1, x2, x3, we would have, and I'm going to write this up above, keep going in front of the computer here, but I'd have x1, let's see, plus 3x4 plus 2x5, this is from row 1, x1 plus 3x4 plus 2x5 equals 0. So in other words, that one's a color for this. x1 is equal to -3x4 minus 2x5. Okay. x2 minus x4 minus 2x5 equals 0. So that tells us, I'm going to get another color, that x2 is equal to x4 plus 2x5. Okay, so that means that for any vector in the null space, our vector x, which is going to have 5 entries, x1, x2, x3, x4, x5, will equal, okay, so x1 is negative 3x4 minus 2x5. X2 is equal to x4 plus 2x5. X3, oh, I never wrote the equation for x3. So what do we know about x3? x3 minus x5 equals 0. So x3 equals x5. So x3 right here equals x5. And then x4 and x5 are our free variables. So we could break that down into x4 times the vector negative 3, 1, 0, 1, 0, plus x5 times the vector negative 2, 2, 1, 0, 1. And so these two vectors are going to constitute a basis for the null space of this matrix. I know that because, well, first I can tell by my work here that these two vectors span the null space, and also neither one of these is a scalar multiple of the other. I have two vectors, and if I have 0 in this entry and 1 in this entry, there's no way that this second vector is a multiple of the first or vice versa. So I'm confident that they're linearly independent. So the dimension of the null space here, let me write it up here, the dimension of the null space of A is 2. We know that now. Now we want to think about the dimension of the column space. And I can do that without writing a bunch of work. So let's focus on the reduced echelon form here. I'm looking for my eraser. And so, I mean, now that we found a basis for the null space, here, I'm going to erase that. And I think what I'd like to do is copy the reduced form. I'm realizing I probably shouldn't have erased it. But I want to copy, it's okay, I have it saved. Our F form of the matrix A is, what did we just have? I know for sure we had this. I remember this much. And then the rest of it, hang on guys. Okay, so 3, 2 here. And then negative 1, negative 2. And then 0, negative 1. Yes. Okay. So here's the row reduced form that we found a minute ago. I'm wondering now about the dimension of the column space of A. That's the question that we have not answered from this example problem. Now remember that to find a basis for a column space, you look at the pivot columns for the reduced form of A, and then the corresponding columns of your original matrix A. So these 3 columns would be your basis for the column space of A. So that basis is going to have 3 vectors in it. So the dimension of the column space of A is 3. Now I want to make an observation about this problem in general. So when you have, let's say, an m by n matrix, and you row reduce it, the pivot columns are always going to correspond to your basis for the column space. So the dimension of the column space for any, if A is any m by n matrix, the dimension of the column space of A is going to equal the number of pivot columns. Because that's just how we find a basis for the column space of A. You look at the pivot columns, you go to the corresponding columns of A. So your number of elements in the basis will always be the number of pivots. Now let's think about the dimension of the null space of A. So if you, I know it's erased now, but if you think about the way that we found the dimension of the null space. So we found first the parametric form for the solution set to the equation AX equals 0. When we did that, so we noticed that these two columns correspond to free variables, right? In the equation AX equals 0. So the free variables are what end up being your parameters when you write out the parametric form for that solution set. And so when you break that down, so you write your parametric form for the solution set, we would have 2 parameters. So when we write our spanning set, we're going to have 2 elements in it, and that's going to be the basis for the null space. So the dimension of the null space is actually equal to the number of non-pivot columns, because those non-pivot columns correspond to your parameters. And so it's always true that the dimension of the column space plus the dimension of the null space should equal the number of columns overall, so n. And that's what's called the rank equation for a matrix A. It's just the fact that the dimension of the null space plus the dimension of the dimension of the column space plus the dimension of the null space will always add up to the total number of columns in the matrix, because column space corresponds to pivot columns, null space corresponds to, the dimension of the null space is equal to the number of non-pivot columns. And so pivot columns plus non-pivot columns, that's just all the columns. And so that's where you get the rank equation.